Hi kids, in this video we are going to continue with measurements and experimentation class 9 physics, and we'll look at simple pendulum in this video. So first of all, look at the definition which is given in your book of a simple pendulum, and there are many flaws in that. बहुत कुछ गलत है वहाँ पे. Just look carefully. When we talk about a simple pendulum, what is a simple pendulum? In ideal case, a heavy point mass suspended from a rigid support using an inextensible and massless string that is known as simple pendulum. But if you look at two things over here, a heavy point mass तो heavy होगा ही नहीं, so this is not possible, isn't it? Again, a massless string, this again is not possible, which means you can say that practically simple pendulum does not exist. Yeah, in ideal case we take a simple pendulum with this characteristic. Ideal case means all the predictions are made keeping this in mind, all the predictions are made, but practically this is not possible. So what we are going to study simple pendulum is, suppose this is a rigid support, okay, you have a string which is lightweight but strong, and you suspend a heavy metallic bob or ball over here made of iron or brass, this is known as the bob. This arrangement is our simple pendulum. Clear? Not this one. This is not possible only, because if you see, the string has some mass, and over here we take a solid bob made of iron or brass, so it is not a heavy point mass. This is not a point mass. Am I clear? Now look carefully. This position, suppose this is your O, okay, this position O, where the bob is at rest, is known as mean position of the simple pendulum. Now suppose you displace this bob a little and leave. So what will happen if you displace the bob? Suppose this was O, you take it to A and then you release it. It will show oscillatory motion, isn't it? It will execute oscillatory motion, which is what? To and fro motion. The body moves forward and then backward, tracing the same path. That is your to and fro motion. Now O is your mean position, remember? Position. And A and B are your extreme position. Now look at some definition. Now we'll look at some definition related to this simple pendulum. Now let us see few terms related to simple pendulum. So this is your rigid support. Suppose this is a point of suspension, suspended a solid bob, okay. This is a simple pendulum, this arrangement. Suppose we displace it to A from O, then it will execute a to and fro motion, isn't it? Oscillatory motion. Now, over here, what do you mean by oscillation? Oscillation. One complete to and fro motion of a simple pendulum is known as one oscillation. One complete to and fro motion of a simple pendulum is known as one oscillation. For example, suppose you start from A, then it goes from A to B and back to A. This is my one oscillation. Okay, these are your extreme points. Okay, this is your mean position where the bob is at rest. Okay, this is your extreme end. So from one extreme to another and then back is your one oscillation. Or you can say, if you start from the mean position, suppose, then from mean position O, it goes to suppose B, then again from B it goes to A, then again to the mean position O. This is your one oscillation. Clear? Next, very important, time period. Very easy. The time required to complete one oscillation is known as time period, denoted by capital T, and the unit will be second. That's the time period, how much time it's taking from going from A to B and back to A. That is known as time period. Then comes frequency. Next is frequency. Now, the number of oscillation in 1 second is the frequency of the simple pendulum, and frequency is denoted by F, and the unit is hertz, or you can say per second. That's the unit for frequency. Now there's a relation between time period and frequency. Just see how do we derive this relation between these two. Now we know that in t second, if t is the time period, then in t second number of oscillation is one oscillation. So in 1 second, number of oscillation will be 1 by t oscillation. And according to the definition of frequency, number of oscillation in 1 second is nothing but frequency, which means frequency is equal to 1 by t. This is a very important relation which we are going to use while solving sums. Clear? Now look at few more terms. I'll just rub this part. Amplitude. Now what is amplitude? Just look over here. The distance between mean position where the bob is at rest and one end, which means the extreme, is known as amplitude. In this case you can say OA and OB. This is your amplitude of the simple pendulum. Clear? One more term, effective length. Now what is this? The distance between the point of suspension, which in this case is S, if you look carefully, S, and the center of gravity of the bob. That distance is known as the effective length of a simple pendulum. Am I clear? Now let us look at one more thing, a small information which I should give. The pendulum which you see in a clock is not a simple pendulum. That's a compound pendulum. That's a compound pendulum. That's not a simple pendulum. Okay. Now, since you are in class 9, I'll give you a basic and very easy difference between a simple pendulum and a compound pendulum. In compound pendulum, what happened? The time period and frequency of the compound pendulum depends on mass. Depends on mass and other factors. But in a simple pendulum, the time period does not depends on the mass of the ball. It does not depend. BOD I've written. It does not depend on the mass. So this is one basic difference which you can remember. Clear? Now let us see a relation between time period and the length of the pendulum. Now let us see how the time period of a pendulum is related to its length. Over here, what we do? We take a simple pendulum, displace its bob a little, it executes a to and fro motion. We measure the time for 20 complete oscillation, and then we keep on changing the length. By the help of 20 oscillation, we get the time for one oscillation. That will be your time period, and then we get a quantity L by T square. Suppose we take the length as 25, and we see that the time for 20 oscillation is, suppose, 20 second. This is 25 centimeter. This is 20 second. So the time period will be 20 by 20, that's 1.0, isn't it? Second. And L by T square. L by T square. 25 by 1 will be 25. Done. Now we change the length. We change the length to 36 centimeter. We notice that the time taken for 20 oscillation, if you increase the length, the time also increases, 24 second. This divided by this is 1.2, and L by T square will again give you 25. Okay. Third case, we take 49 centimeter. This will be 28 second, 1.4. Again, this is 25. This, if you look carefully, this quantity L by T square is coming constant. In the fourth case, we take as 64 centimeter. Time for 20 oscillation is 32 second. This will be 1.6. This again is 25. We change it to 81 centimeter. This becomes 36 second. This is 1.8. This remains 25. We take the length, suppose 100 centimeter. It's 40 second. It's 2. It's again 25. Now look carefully. If you can see, if I increase the length of the pendulum 4 times, how many times? 4 times, then the time period also increases, but the time period increases 2 times, twice. Am I clear or not? And the quantity L by T square, is coming constant, which clearly means that, see, length and time are proportional to each other, directly proportional. How? We'll see that. When one increases, the other also increases. Now, this increases 4 times, this increases 2 times, which means T square is directly proportional to the length. T square is directly proportional to the length, which means you can say also length is directly proportional to the, T is directly proportional to the square root of length. We can say this also. So by this experiment, we conclude that the time period of a simple pendulum is directly proportional to the square root of the length of the pendulum. Am I clear? Now let us see the graph. Since L by T square is a constant, so we know if we plot the graph L by T square, we'll get a straight line. Let us see this. Now let us see the graph showing the variation of square of time period T square with the length of the pendulum. Now just now we did T square is directly proportional to the length of the pendulum. Capital T represents a time period. So if they are directly proportional to each other, and we take along the x-axis we take the length of the pendulum, along the y-axis I take T square. Since they are directly proportional to each other, we'll get a straight line, and this is a graph, isn't it? So this is your graph. Now look at the slope. Now what is the slope of a line? Suppose we take 2 points. This is a straight line, okay? L2 over here and here L1. Corresponding to L2, suppose over here you have T1 square, and corresponding to L2, the value over here is T2 square. Okay? So slope of this line will be equal to, we have done change in y coordinates, by change in x coordinate, which means simple. Change in y coordinate is nothing but T1 square minus T2 square, and change in x coordinate is L1 minus L2. So this is the slope of this graph. Now, one thing we know beforehand, that the slope, this slope is constant at a place. This slope, this is constant at a place, and it's given by, the slope is given by 4 pi square by g, where g is your acceleration due to gravity, which means 4 pi square by g will be equal to slope, isn't it, which is T1 square minus T2 square by L1 minus L2, which is equal to what? T1 square minus T2 square by L1 minus L2. With this measurement, we can calculate the value of g, if you look carefully, which means g will be equal to 4 pi square by slope of T square versus length graph, isn't it? So this is, by this method we can get the acceleration due to gravity of a place also, because slope is constant at a place and is given by 4 pi square by g for this graph. Done. Now let us see the factors on which the time period of a pendulum depends. Factors affecting time period. Just now we did one, that the T square is directly proportional to the effective length of the pendulum. T is the time period, which means T is directly proportional to the square root of the length, which means they are directly proportional, which means that if you increase the length of a pendulum, the time period also increases, and if you decrease the length, the time period also decreases. This we notice in pendulum clock. In pendulum clock, what do you notice? I'll tell you. Pendulum clock. That in summers, the clock becomes slow. In winters, the clock becomes fast. Now, how this is possible? All because of length. What happens? I'll tell you. In summer, due to the heat, we know that solid expands. The length of the pendulum increases, which means the time period increases. See, this is your pendulum from A to B. This is your time period. So now in summers what happens? Since the length increases, the time period increases, it will take more time to complete one complete oscillation, which means it will have less number of oscillation in a given time, which means it will slow down. Clear, right? But in winters what happens? The length decreases, the time period also decreases. Now it will have more oscillation in a given period of time, so it becomes fast in winter. Similar is the case when we are on a swing. When we stand, we see that the time period of the swing when we stand on a swing, on a swing, we see that the time period of the swing decreases and the swing moves faster. The swing moves faster. Why this happens? Because when we stand, what happens? The center of gravity of the swing, goes up. So the effective length of the swing decreases. So the time period also decreases. So the swing moves faster when we stand as compared to when we are sitting, where the center of gravity is at a lower position. The effective length is greater. Done? Now, second factor on which the time period depends is acceleration due to gravity. So time period is inversely proportional to square root of acceleration due to gravity, which means if you decrease the acceleration due to gravity, time period increases because it's inversely proportional. If you increase the value of g, the time period decreases. We see that the pendulum clock, when taken on mountains or inside mines, or in mines. Now, first of all, though, when you talk about mountains or mines, the value of g is less over there. The value of g is less, which means time period will be more. So the clock goes slow. Simple. Am I clear? The clock goes slow because the value of g decreases and time period increases. Clear, eh? So the clock goes slow. Done? Now the third thing we'll see, time period is independent on the mass of the bob. Doesn't matter what is the dimension of the bob, doesn't matter. The time period does not depend on that. Okay, then one more thing we'll discuss. Time period is independent of the extent of swing of the pendulum, which means it's independent of the amplitude. Am I clear? So combining these two, we see that, again remember that it is directly proportional to the square root of the length, inversely proportional to the square root of the acceleration due to gravity. It's independent on the mass and it's independent of the amplitude, the extent of swing, you can see. So combining these, we get to a conclusion that time period, remember this, time period of a simple pendulum is 2 pi root over L by G. where G is your acceleration due to gravity, L is the effective length of the simple pendulum. While doing numericals, we'll use this. And one more thing, the last thing you can say, a second pendulum. Seconds pendulum, as the name suggests, a pendulum whose time period is 2 seconds, which means from A to B it takes 1 second, and from B to A it takes another 1 second. That type of pendulum is known as a seconds pendulum. And if you put the value of t as 2 and calculate the length of the second pendulum, it's nearly 1 meter. Okay, I hope this is clear. What is a second pendulum? This kind of pendulum, you can say, in the pendulum clock you have this only, where it takes 1 second to move from A to B. Done. So this was the end of this chapter, I think. In the next class, in the next video, we'll see hopefully the numericals of this chapter. Till then, take care. And if you haven't subscribed the channel, do subscribe it.